Onward with biodiversity. First of all, we need to talk a little bit about the Tertiary, in that it is an outdated term. It's only recently become outdated, which makes it a little bit of a problem because you'll see it regularly in the literature, perhaps more commonly than the new names Paleogene and Neogene. This was formerly the period of time between the end of the Cretaceous, when the mass extinction occurred, and about 1.88 million years ago. Now the Tertiary period is broken up into the Paleogene from 65 to 23 million years ago, and the Neogene from 23 to 2.6 million years ago, followed by the Quaternary period from 2.6 million years ago to the present. For some stratigraphic reason, the Tertiary period has been eliminated and renamed. Quaternary period remains with the same name, but a different time scale. It's gone from starting about 1.8 million years ago to 2.6 million. And put all this together, it's known as the Age of the Mammals. And we can see in this image kind of a Pixar Paleogene review of biodiversity. You can see some large mammals, some large birds, and some smaller mammals lurking in the distance. And these are early horses here. We need to remember that continental positions and ocean circulation have changed significantly between the present and the past. If we go back to the Paleogene, we can see that continents are roughly in the same position as today, but large portions of continents were covered by shallow water. Much of the Middle East was underwater at this time, not ironically where a lot of petroleum is located today. Petroleum, the rich deposits here, were laid down in these shallow seawaters. Same goes with North Africa, the northern coast of South America, the southern coast of North America as well, and off the coast of Mexico. These shallow waters often led to the appropriate conditions for organic matter to be retained, stored in the sediment rock record, and heated under pressure to the right temperature to generate petroleum. Now, there is some ocean circulation information here, but I wouldn't take it too seriously. One thing to take seriously is this gap between North America and South America. It was the closing of this gap when Panama finally became Panama that circulation stopped running between North and South America, and this resulted in significant climate change for both continents and the rest of the world, starting about 2.6 or so million years ago. Now, the Cretaceous came to an end, a very dramatic, devastating end, at the beginning of the Paleogene. This is the KT boundary extinction, which we now call the KPG extinction, that occurred 65 million years ago. It was caused by, or maybe made worse, by the impact of a multi-mile wide asteroid that created a large crater that's located in Chixulub on the Yucatan Peninsula. And about half of it is on land and the other half is under the Gulf of Mexico. So this extinction, we lost a number of famous fossils, and people have argued for years, for well over 100 years, as to what caused this extinction event. Some people argued that climate change was the main proponent, or the volcanic eruptions in India, the Deccan Traps, were responsible. We'll get back to that in a few minutes. Regardless, the extinction killed 16% of marine families, about 50% of marine genera, and about 20% of land vertebrate families, including the non-bird dinosaurs. A couple examples here. Ammonites went extinct. These are creatures that appear similar to what we see today in an animal called a nautilus. The fossils are quite valuable at times. This is a fossil recovered from the Bear Paw Formation in Alberta, the Cretaceous Bear Paw Formation. It is on sale right now for $280,000 US with free delivery if you're interested. This is a mosasaur, a marine reptile, a very large. A person would just about fit in the mouth standing up here. These teeth are available for sale online for a much more reasonable price of about $25 to $30 for a large tooth. This would be, if you're looking at your computer and it was the same size as my computer, This is about life size. So about the size of your hand, depending on the size of your hand. At the end of the Triassic, about 200 million years ago, we had another mass extinction. In this case, the mass extinction was caused by massive eruptions of lava along the east coast of North America, the west coast of Africa, the Central Atlantic Magmatic Province. This is related to the opening of the Atlantic Ocean as Pangaea was breaking up. The volcanic event probably led to global warming. Enormous amounts of CO2, other gases were released from this fissure-type eruption as it ripped open Pangaea. Rocks from these eruptions can be found in the eastern United States. New Jersey is a good place to look. Eastern Brazil, North Africa, and Spain. The loss of life includes about 20% of marine families, about half of the marine genera, again. And we don't know much about vertebrates because the fossil record is so bad, so we don't really have a good idea of the effect of extinction on the vertebrates. A couple notable losses were brachiopods. Nearly all species of brachiopods went extinct, except this one genera, Lingula, that survives to this day in really stinky brackish waters. Another notable loss was the loss of conodonts. Until recently, we didn't really know what these were. We had our suspicions that were ultimately mostly correct. You can see some examples here. These are called elements. These are little phosphatic features or structures that are morphologically distinct. Each species of conodont had a very unique set of these in its head. They're positioned on the head of a pin here for scale, so they're very, very tiny. They've been really important for biostratigraphy because many of these species appear, spread around the world, and then disappear in a short period of time. That makes them ideal as an index fossil. And because the color changes with temperature changes, we can use these as indicators of the maturity of petroleum resources. So when drilling at an oil well, you would recover fossils like these, and they would tell you whether you're on the right track to making some money. Now, the Permo-Triassic Extinction is the big one, by far the largest mass extinction that we have characterized to some degree. About 251 million years ago, we suspect that a comet or an asteroid was the culprit, and that's out of laziness in reality. It's unlikely that's the cause anymore. It was believed that until recently. Other people believe the cause was flood volcanism from the Siberian Traps, very, very large volcanic deposits, and the related loss of oxygen in the oceans. Others believe the impact triggered the volcanism and may have also done so during the Cretaceous-Tertiary Extinction, or the Cretaceous-PG Extinction, the KPG. So here we have a bit of an odd situation in that massive lava flows are present for both the Permo-Triassic Extinction and the KPG Extinction. The Permo-Triassic Extinction was the worst. About 95% of species were wiped out, over 50% of marine families, 84% of marine genera, and an estimated 70% of land species that include plants, insects, and vertebrates. Other culprits include clathrates. These are a weird kind of methane gas ice that forms under specific conditions. If those conditions change, these clathrates are destabilized and the ice becomes methane gas. Large pulses of hydrogen sulfide from what's called a Strangelove ocean or a dead ocean could have led to an extinction event as well. However, just recently, people have begun to look in a different way at these Siberian traps. These Siberian traps in northern and central Siberia, here you have an outline of the United States for scale, were roughly the size of the United States, the continental United States. And it so happens that these traps, this lava outflow, took place from beneath petroleum and coal deposits. So now we're producing an enormous amount of magma and we're pushing it through petroleum and we're pushing it through coal, and that's going to heat that organic matter up. And as soon as it reaches the surface, that very hot material, the gases that are exuded, are going to hit the oxygen in the atmosphere, and you get these fire fountains they described as occurring every few kilometers or so. So essentially an area the size of the continental United States is on fire. That's a big deal. And the dust that's generated by this gigantic United States-sized fire, the dust is going to enter the stratosphere where it's no longer being cleaned out by precipitation. So it stays there. It stays there for years. And as that dust eventually settles from the atmosphere, there's nothing to bounce incoming radiation back into space. With this enormous amount of CO2 that we've introduced from the burning of all this material, we go from a cold period when the atmosphere was dusty and dark to a hot period. So the climate is totally out of control. And this is exactly the kind of thing that would cause mass hysteria in humans today and mass death, mass extinction in all other organisms in the past and or today. In the late Devonian, we had some important evolutionary events take place. We had the evolution of Ichthyostega here. This was a very important transitionary form between fish and land animals. It occupied the freshwater river environments of a number of locations from 374 to about 360 million years ago. It went extinct at the end of the Devonian. And then about the same time, a little bit before, we have the Tiktaalik at 375 million years ago. This was discovered just recently here on Ellesmere Island in northernmost Canada. So when we look at the taxonomy of fishes here, evolving into four-legged animals, we see Ichthyostega pop out here. We see divergence taking place here with one branch leading to Tiktaalik and another branch leading to Ichthyostega. Ultimately, we can look at this in another way, and we can see that at this point we had a common ancestor between the Tiktaalik, the amphibians, the mammals, lizards, and other modern organisms, including us. And we're grouped here with the elephants, the four-legged animals. So this radiation event took place here around 375 million years ago, leading to us. The late Devonian came with another extinction about 364 million years ago, a little bit before the end of the Devonian. We don't know what caused it. It was very significant. It killed 22% of marine families, about 60% of marine genera. We just don't know much at all what's going on land at the time, so can't really talk about it. Two major organisms that went extinct at this time include the stromatoporoids. You can see here, these are layered cellular structures. These were very common around the world, went extinct in the late Devonian extinction. And maybe a more famous example, Dunkleosteus, the bone-headed fish, a very, very large bone-headed fish, went extinct. This fossil was recovered from the highway construction around Cleveland, I believe. It's either Cleveland or Mansfield, Ohio. So anyway, north central Ohio. Here is a woman for scale with a bone-headed fish. We're not really sure how they maintained buoyancy in the water, given these gigantic, thick, heavy, bony plates. But nonetheless, they went extinct in the late Devonian extinction. At the end of the Ordovician-Silurian mass extinction took place about 439 million years ago, was related to rapidly changing sea level. Sea level dropped rapidly when we had the onset of a glaciation. It rose rapidly for reasons that I don't understand at this point. And then it went down again rapidly. So we had two massive glaciations appearing close together, resulting in 25% of marine families and about 60% of marine genera being wiped out. The Hirnantian Extinction is the cold terminal end of the Ordovician period. And it's named after the Cum Hirnant. Cum is a Welsh word. In the Welsh alphabet, the W is a vowel. Sounds like an oo, o, cum is a valley. This period was investigated by us. This is Chris Holmden. Dan Laporte was our grad student. I was doing all the digging. After digging these 1 meter deep pits all the way up this hill, these knuckleheads up here realized we were in the wrong place, and we dumped all of our bags of rock out and got in the Jeeps and drove around the other side of the mountain. It's awesome. What did we learn? Well, we learned that the carbon isotope value of organisms that were present at this time show this glacial episode. So we have a decrease in sea level represented by this rise in carbon isotope values, increase in sea level, very short, very sharp. We analyze the sample over and over again, and it comes out the same, so it's not a fluke. And then back to glacial, and then a decline in the glacial towards the modern, into the Silurian. So the end of the Ordovician occurs right about here. The Cretaceous-Paleogene mass extinction is kind of special because it's closer to the modern. We have a lot more of a rich fossil record for this than we do any of the other mass extinctions. Again, this occurred 65 million years ago. About 50 to 75% of species went extinct at this time. Scientists have been arguing for a long time about the causes. The four most recent ideas that at least survived until recently include sea level change, like we saw in the Ordovician, sharp temperature changes, like we saw in the Ordovician, volcanic eruptions, like we see in the Permo-Triassic, and bollide impacts, large extraterrestrial bodies striking the Earth. We see evidence for those around the Earth in a number of locations. So we'll start out with sea level change and climate change. This used to be the number one theory because it's the easiest to get your head around. It remains the number one cause for extinction only for the post-Ordovician extinction, the Hirnantian extinction event that we just talked about. In fact, when you look at it, the largest sea level fluctuations often occur with few species lost. So sea level rises, shallow water organisms move inland. When sea level falls, shallow water organisms move seaward. And your book talks about climate change theory in kind of a dismissive way. It's been a long time since I read the book, so I don't remember quite what they said. But we'll get back to this climate change relationship to extinctions in a few minutes. If the extinction event is caused by the impact of a bollide, an asteroid or a meteor, versus volcanic eruptions, we look for a couple different things to differentiate between the two. In 1979, an Iridium Anomaly was discovered in Gubbio, Italy, and this was a really big event, huge event, and it was known as the smoking gun that killed the dinosaurs. Supporters of this theory provided a number of predictions that would serve as a test for the theory. If this was a worldwide event, we should find iridium around the world. The Iridium Anomaly should be found worldwide, and it has been found in 75 locations globally. It's been estimated that a 10-kilometer wide body would be required to generate that iridium layer around the world. This enrichment should always be found within the same interval of geologic time. And indeed, all iridium layers are found within polarity chron C29R. This is a magnetic period from 65.6 million years ago to 65.9 million years ago. So these researchers put the extinction event at 65 million years ago. Number 3, large meteorites strike the Earth sufficiently frequently to explain the extinction record. An astronomer named Eugene Shoemaker demonstrated a relationship between the frequency and size of impacts. Large things hit the Earth seldom. Small things hit the Earth very, very regularly. It's believed that a 10-kilometer wide bollide should strike the Earth about every 100 million years. In 1908, it was probably a small comet that exploded over Tunguska, Siberia, that caused the damage you see in these images here. Now, these images were taken in, I think, 1927, a long time after 1908. People finally got into this region, which is really, really remote in Siberia, and took these photos and looked for bits and pieces of whatever hit the Earth. Haven't found it yet, but they're still looking. Number 4, on shorter time scales, events like these should be rare. In polarity chron C29R, there are no other iridium enrichments. The 35 million year period around the KPG boundary has no other anomalies, in fact. Now, if we look at the statistics behind impacts, we can see tiny impactors, little grains of sand, or maybe even things smaller than that, striking the space shuttle. I was invited over to Siberia a few years ago to Novosibirsk, and they took me to a history museum. And while we were there, I was handed the windshield from Yuri Gagarin's spacecraft. So he's the first person in space. And his windscreen, the little window, which is about the size of a head of lettuce, had a little crater in it from one of these impactors. A grain of sand hitting it 40, 50,000 miles an hour. And that's just a weird thing in Siberia. They'll hand you something like that. You know, total stranger here. You want to hold the windshield from the first person in space. So we can look up at night. We'll see shooting stars. Those are pretty common. Meteorites, big meteorites strike the Earth about once a year. Craters like the Winslow meteor crater here in Arizona hit the Earth about every 10,000 years. And then the large, huge structure in Sudbury, Ontario, that's so important for the nickel industry there, much less frequently. There's a little town here near Meteor Crater, which is known as Meteor Crater. So you can drive right up here. The visitor center is located right about here. I think it's like $15 to go in there. You're not allowed to go down here, but they have a fake display where you can act like you're standing down here. It's free. Okay, the Manicouagan structure is the largest easily visible structure on Earth, about 100 kilometers in diameter. And this happened about 215 million years ago. So we took a motorcycle trip through Labrador and Quebec a few years back, and 1,200 kilometers of dirt and mud road finally turns to pavement right here. I'm getting in touch with the roadway again. And this is a view of the lake taken from right about here, looking over to here. So a very considerable structure. And the reason we see it so clearly is because of this. This is the Manic 5 hydro facility, an enormous dam that is located down around somewhere down here. So they built this dam, they allowed the reservoir to fill up, and a nice watery donut appears that, again, is about 100 kilometers in diameter. Number 5, plants as well as animals should have suffered as a result of the meteorite impact. There is very significant evidence of turnover in the types of vegetation inhabiting land surface. This is unlike the Devonian, when we had few land plants. We now have tens of thousands of species of land plants. And much of this work is based on spore and pollen research. So what you can see here, the iridium abundance spikes right at the boundary, and the pollen to spore ratio changes dramatically at that same boundary. So the pollen goes away. The spores come back first. The opportunists, the pioneering species, are going to be spore producers as opposed to pollen producers. Most of the flowering plants got knocked down at the end of Cretaceous period, the angiosperms. Number 6, the gross or bulk chemical composition of the boundary clays should be identical worldwide, given that they all originate from the same excavated material. This is true. When we analyze material geochemically from around the world, it looks the same. Number 7, the boundary clays should differ in composition from more typical clays deposited above and below the boundary clays at individual sites. Yes, this is true as well. So it's an anomaly from what's above and what's below. It's different. Any chemical or isotopic signature in the boundary clay will have a significant extraterrestrial component. The Iridium Anomaly is the best studied of these anomalies, but others could also be extraterrestrial. Number 9, the boundary clay should bear some evidence of the high temperatures generated during impact. And we do see that as well. Spherules of silicate minerals have been found in these layers. So these would have been made from material that's blasted into the atmosphere in a molten state, and because it's falling through the atmosphere, has a chance to cool without being affected extensively by gravity. So they tend to form these little spheres. Number 10, the boundary clay should bear some evidence of the high pressures generated during impact. Yes, that is observed as well. When we look at fractured grains of quartz, we can see stress lines in the polarity of the light that is traveling through these crystals. So this is evidence of pressure that wouldn't be generated by a volcanic event. This is a bit controversial still. Number 11, the KT event should have generated wildfires that left a sedimentary record of charred material. Charcoal is found at the boundary layer, but I would argue that charcoal is found wherever you look for charcoal. There are a lot of fires right now in California. That soot is spreading around the world. And if we look for that soot, we would find it. Number 12, the iridium-rich layer should be just above the last dinosaur fossil. Dinosaur remains have been found within a couple meters of the boundary, but due to the rareness of the dinosaurs, we encounter what's called the Signor-Lipps effect. This is just that if things are rare, you don't expect to find a continuous deposit of them. And we know that dinosaurs are rare in general, which is why people are willing to pay so much for a dinosaur skeleton. Number 13, the pattern of extinction should show no evidence of preferential survival of species that were well adapted to the Cretaceous environment. Most mass extinctions are nonspecific, particularly the KT extinction. Almost all land mammals larger than 25 kilograms became extinct. The volcanic theory of mass extinction is supported by much of the same evidence as the extraterrestrial theory, so this brings some of these into conflict. The Deccan basalts may have played a role in the extinction of the dinosaurs, and it may have been the primary role, or it may have been a secondary role. Most of this basalt was erupted between 65 and 60 million years ago. Gases released by this eruption could have changed the global climate and led to this mass extinction event. The deposits in India aren't quite as big as the deposits in Siberia, but they are very, very significant. You can see that some of the layering here of this basalt. These Deccan Traps are one of the largest volcanic provinces in the world, more than 6,500 feet or more than 2,000 meters of basalt lava flows, covering an area of 200,000 square miles or 500,000 square kilometers, the size of Washington and Oregon State combined, or for our purposes, close to the size of Saskatchewan and Manitoba. The volume of basalt is estimated to be over 12,000 cubic miles or 512,000 cubic kilometers. For comparison's sake, the 1980 eruption of Mount St. Helens generated 1 cubic kilometer of volcanic material. 1 versus 512,000. When I was 16, I did a science fair project, an isotope project on kind of microevolution using radioactive phosphorus and a couple other things. And me and my friend ended up getting sent out to California, where we met a couple of Nobel Prize winners, including Luis Alvarez and his son Walter. And we got to talk about this dinosaur extinction the day before it was announced to the rest of the world. So it was kind of cool hearing it, and then it was in every newspaper, every radio show, TV. There was no internet, but it was everywhere else. We suddenly realized, hey, this is important, I guess. It was. So Walter Alvarez has proposed evidence against the volcanic theory. Number 1, sand-sized spherules, even if ejected by volcanoes, would not reach ballistic orbits as impact ejecta do. Because of that, they're not going to be widely distributed. The KT spherules are widely distributed around the world. Number 2, shocked quartz, the kind found at the KT or KPG boundary, has never been found in deposits of volcanic origin, but is common in deposits with known impact craters. Number 3, volcanic ejecta tend to have very low iridium concentrations. It was noted that Fullerenes, 60 carbon atom buckyballs, contain helium-3, which is more common in outer space than it is on Earth. So these weird buckyballs, you can look up Buckminster Fuller at some point, kind of a weird, interesting character who's responsible for this name. Well, it was named after him. So they form little cages for this weird helium-3 atom. This is very likely an extraterrestrial source. Okay, so the smoking gun, the Chixulub crater, was discovered in the 1990s, determined to be about the right age for end Cretaceous bollide impact. The structure is about 200 kilometers in diameter, about twice the size of the Manicouagan feature that we saw in Canada. It's one of the largest craters that's visible on any body in the solar system. This is a horizontal gradient map of the Chixulub crater. You can see the location of cenotes. A cenote is a collapsed cave. This is all limestone here in the Yucatan Peninsula. And it was shocked and fractured and cracked by this impact. And where those fractures and cracks appear, we have dissolution of the limestone. We have caves form, and eventually those caves are going to collapse. When they collapse, the sinkhole becomes a cenote. So we can see cenotes forming these rings that correspond to the rings surrounding the impactor here, the center of the crater. Discovered by Mexican petroleum exploration and by some people working out of Canada. This is a three-dimensional map showing you the same thing. Here we have the crater center. This is a bit like if you drop a pebble or say drop a skittle into a cup of coffee. You'll see the surface deform downward and then respond. It'll rebound in the center. And in this case, it rebounds and it solidifies, and a permanent record of this droplet remains. Environmental impacts of the meteorite impact include a change from a low equator to pole temperature gradient. There was no ice at the poles at this time. The Earth had an equable climate. It was not much cooler at the high latitudes than it was at the lower latitudes. And dinosaurs lived close to polar latitudes, but weren't as common as a few tens of millions of years earlier. So that implies that temperatures were going down slowly for tens of millions of years leading up to this impact event. A large meteorite passing through the atmosphere would have converted nitrogen gas to nitric oxide, which would have destroyed the ozone layer. So now we're exposing all of the survivors to ionizing radiation. Anything living in the Yucatan would have been destroyed instantly. A 200-kilometer crater would have been tossed into the atmosphere at a high temperature. This material would quickly circulate around the world. As the impact ejecta passes back through the atmosphere, the air would become heated and potentially fires ignited. The soot that enters the atmosphere would be accompanied by sulfuric acid. This would be generated by the volatilization of anhydrite in the Yucatan. This is CaSO4, nearly the same kind of stuff that drywall is made of. Both of these would block sunlight, the volatilized anhydrite and the sulfuric acid. The atmosphere of Venus is sulfuric acid, so think about that as an example. Huge tsunamis, 150 meters, would be generated that would destroy coastlines for hundreds to thousands of kilometers, maybe globally. The blocking of sunlight would kill off plants, cooling the climate, leading to what was back in the 80s known as a nuclear winter. Acidic snow would fall and climate would remain cold for 6 months or more. We don't know how long for a number of reasons. Thousands of gigatons of carbon dioxide would be released as limestone is volatilized. That could have caused temperatures to increase by 10 to 15 degrees centigrade. Very, very significant. So we've punched the Earth. We have filled the atmosphere with dust and acid, shutting off sunlight, leading to a cold period. And when that material is removed from the atmosphere, it clears up. Now it's full of CO2 and temperature goes way up.